Hi, I'm Tarana Tabassum and I'm presenting our time series analysis course project on behalf of my group African Coffin Lifters. We chose a very familiar issue to work with, Melbourne's weather. Our dear Melbourne is best known for its fickle weather. The city has been described as having 4 seasons in one day, but it can still be enjoyed all year round if planned well ahead. So we chose a dataset from Kaggle.com called Rain in Australia that focuses on Australia's weather readings. The dataset was originally prepared for rainfall prediction, but we forecasted Melbourne's maximum temperature from it. Here's a view of the dataset from while we were working with it on RStudio. This data gives us readings for daily log of temperature and other weather conditions like precipitation, humidity, wind pressure, etc. from 2008 to 2017 from all around Australia. As it can be seen, it was a daily dataset. To work with it, we converted it to yearly data and selected only Melbourne's yearly average maximum temperature. Based on this, we forecasted Melbourne's yearly average maximum temperature for the next 10 years, 2018 to 2027. On the right-hand side figure, we see a view of the plot after it was converted to a time series. Here, it's grouped by year and plotted as time series data. We find some important observations from this plot. Firstly, there is an upward trend and no fluctuations around the mean level. Secondly, it appears that this series is autoregressive as there are multiple succeeding points, but there's no moving average. But we also observe absence of seasonality in this time series. Also, it is possible that there is a slight change in variance depicted by the movement of values. And the plot on our left shows yearly 31% correlation within Melbourne's maximum temperature. Next, we tried fitting multiple models for the time series data on hand. We concluded that the linear trend model seems to be the best fit for this data, with a higher R-squared value and a lower p-value. The F statistic generally shows the overall significance of a model, and in this case, it was significant. In the middle plot here, we see a visualization of residuals, from where we can imply that the residuals still do not capture a change in variance. According to the model summary, about 57% of the variance in this time series is explained by this linear trend. This adjusted R-squared value is good enough, but could possibly be improved. The R-squared value is defined as the square of the sample correlation coefficient between the observed series and the estimated trend. It is also the fraction of the variation in the series that is explained by the estimated trend. On the left, we have a QQ plot for the linear trend model. Non-normality can be assessed using a QQ plot. With normally distributed values, a QQ plot looks approximately like a straight line. But in this QQ plot, as expected, we can see a departure from normality in some parts of the distribution. On the right-hand side, we see the plot of ACF. We can use sample autocorrelation function ACF for the standardized residuals to identify values of autocorrelation with its slacked values. In simple terms, it describes how well the present value of the series is related with its past values. We can see on this ACF plot that there is no lag, which means that there is no significant dependence here. After all these tests and summarization, we decided that the linear trend model is the best fit for this data because we found a smaller significant p-value of 0.007 for this trend, which was 0.03 for the quadratic trend. This adjusted R-square value was 57%, which was 50% for the quadratic model. So we decided that the linear trend model is the best fit. As we noticed before that the time series data indicated non-stationarity, we did Box-Cox transformation first and later used differencing to make it normally distributed. This is how the series looks after first differencing. As we go through an ADF test and create ACF and PACF plots after differencing, we find that there is no more non-stationarity. It can also be seen here that the year 2009 recorded the highest temperature in the history of Melbourne's weather, and there is a sharp drop after that. But it was because of an unusual occurrence, a heat wave which took place in the Tasman Sea. We cannot take that variance into account as it surely wasn't a regular incidence. The plot also tells us that the series is in an upward moving trend with very less changing variance now. Next up, to forecast the next 10 years temperature, we first need to select a fitting ARIMA model for these time series. So here we draw an EACF and BIC table through RStudio, and here's how they looked. We chose models 111, 110, 011 from EACF table and 111, 112, 211, 212 from BIC table. Further, we ran z-test of coefficients for parameter estimation on each of them to find out which models are significant. We performed residual analysis for all of them to find out which model fits the best. Lastly, to conclude on our best ARIMA model, we sorted the AIC and BIC values of all the probable models. The model 011 with the least value among all the models was chosen as the best fit. Using this model on predict function in RStudio, we forecasted the average maximum temperature for the years 2018 to 2027 for Melbourne City. As we can see in the forecasted plot, the average temperature for the next 10 years turns out to be 22 degrees Celsius. This is almost unchanged from the last 10 years, which means we Melbournians are not going to suffer too much till 2027. So that's all from us, presenting Melbourne's average maximum temperature for the next 10 years. Thank you.